So we've talked about exponential functions. Now we're going to model with them, which means that we will need to use, it says at the beginning of this section, it says we're going to find regressions based on data and create exponential functions without the use of graphing software. So that's true, but first we're going to use graphing software so I can show you how to find it that way also. So we have this information. We need to find the exponential regression that models this set of data. Now, if you look, right, there's not a value for 0, so we can't use that point, but we can use all of the others and type it into Desmos. So I have conveniently typed it into Desmos. So here we have the graph. We got these points. We need to figure out what the regression equation is. So we're going to do what we did before. We're going to come over here to this little button, and we're not going to use linear regression because we don't want linear regression. We want the exponential regression. So we're going to change this to exponential. It's that simple. There's our equation. Okay, so that's what we're going to write down on our paper, but that's how you find it. So let's come back to our paper. The regression is y equals 0. It was 9.836 times 2.004 to the x. That's it. X is the number of months, y is the number of rabbits. So now we'll use this equation. How many rabbits would you expect to have been present at month 0? Well, if x is 0, then this term goes to 1 because that's what happens when you cancel that out. And you're left with this number right here, so this 9.836. So that means that our initial population is 9.836. So it's going to be somewhere between 9 and 10 rabbits because we're talking about actual rabbits, right? You can't have part of a rabbit. So the answer would be somewhere, or we should expect between 9 and 10 rabbits. And anytime we find a regression, we're normally looking at something else also to use that regression equation. So now we're going to use that regression equation to find the number of rabbits at the end of year 1. And all that means is that we're going to take the number 1, we're going to plug it in right there and call it, or I'm sorry, that's not true. We're talking about months. We're talking about months. So at the end of 1 year, how many months have passed? Well, 12 months have passed. So that means that y is going to equal 9.836 times 2.004 to the 12th power. When you take that and type it into an equation, you into a calculator, you get 41,261 rabbits. That is a lot of rabbits. But that's how we deal with those real world situations. Now let's talk about what happens if you don't have a calculator because you have to do this by hand. We know that this is our equation. We also know that a is the initial value. And if you look at both of these problems, we have an initial value given. Our initial value is 18 here and 4 here. So that means in part A will be 18 because that comes from this point. In part B, A will be 4 because, again, that comes from this point. So we really just need to find the B value. So if we're just finding the B value, then we know that y equals 18 times b to the x. That's when this other point comes into play. So we're going to use this x and this y and plug them in and solve for b. So if y is 4,608, then that will equal 18b to the 8th power because that was the one that's in the problem. Now we're going to have to solve this. This is an equation just like any other equation. So we need to get b by itself, which means we need to get rid of the 18 first. So we're going to divide both sides by 18. When you divide 4,608 by 18, you get 256. Okay, now we're going to have to figure out, well, what power of 8 on what base gives us 256? 256 is not a huge number, believe it or not. So if we're talking about raising something to the 8th power, we need it to be reasonable. So let's use a calculator and let's guess, right? It's not 1 because 1 to any power is just 1. So let's do 2. 2 to the 8th power. Well, that's 256, which means that b has to be 2. The good news is that when you're doing your practice over this, for the most part, you're going to end up with some whole numbers. So it will be, call it guessable, right? Because 2 to the 8th power is 256, b is 2. which means that our final answer is y equals 18 times 2 to the x. Remember, x and y are still going to be variables, but a and b are plugged in. Let's do another one. So same thing, a is 4, we know that because that's what we started with, and we know that y then will equal 4 times b to the x power, where we're solving for b. Well, we're going to solve for b by using this point, x comma y. So that means 100 is going to equal 4b to the second power. And that's what we'll have to solve. So let's get rid of this 4 by dividing by 4. 100 divided by 4 is 25. And we're left with b squared. Now, what will b have to be in order for something squared to equal 25? So what squared equals 25? Well, 5 squared equals 25, which means that b is going to be 5, which means that our final answer is 4 times 5 to the x. Now, you should notice in the problem on the right, where we have this right here, I put 4 times 5 to the x. Here I put 18, and then in parentheses 2 to the x. Those are two different ways to write the exact same thing. Just keep in mind, you will never put 18 and 2 together. You will never put 4 and 5 together because those are not like terms. 5 here is being raised to the x, not 4, so you can't put them together. Now we have one more word problem, and like in the last section, we're going to have to use a formula that represents something, and we'll plug things in. So the formula we're going to use for this problem is actually f of t equals a 0.5 to the t over h. A is still your initial, right? Your principal, that hasn't changed. That's the same as it was before. H is the half-life. Okay, and what that means is, and we're going to see this in this problem, it's how long it takes for the item, isotope, element, whatever, to decrease by half. And in this problem, there's only 2 numbers to look at. We're talking about element X. It's a radioactive isotope such that every 17 years its mass is decreased by half. So that means that's exactly what I'm talking about, right? This is H. Given that the initial mass of a sample is 30 grams, that's your initial, right? So that means that's A. Write a function showing the mass of the sample remaining after t years. So very much like the problem we did in the last set of notes, we're going to take these numbers and plug them in. So that means f of t is going to equal our A, which was 30, times 0.5 to the t over our h value, which was 17. Now again, just like last time, we're going to have to take this 17 that's in the denominator of our exponent, we're going to have to push it into the 0.5. So we're going to have to do something like this. So we're going to have this, we're going to have 0.5, we're going to raise that to the 1 over 17th power times t. Now the reason it's 1 over 17 is because that 17 is in a denominator, right? Right here, it's in a denominator with t. That means over here, it still has to be in a denominator, so it doesn't just magically move to the top. It's not to the 17th power, it's to the 1 over 17th power, and that's a very important distinction. Then we're just multiplying, right? You throw that into a calculator, and you get 0.9903 to the t. The last thing we need to know is the rate of decay per year, and that's going to be determined, so the decay rate, and we talked about this also, is 1 minus whatever that number is. So 0.9903, which is 0.0097, and that's not a decimal. That's a decimal, so it's not a percent, and it wants it to be a percentage. So the decay rate would be 0.97, because you move it over there, percent decrease per year.